Like trying to like download the game.
Yeah.
Okay, let's talk about the test. So, what were there? There were 5 questions, is that correct? Yes. All right, so the way that I came up with your grade is I graded just the first 4, all right? Only 1 or possibly 2 people got number 5 right. Okay, so I have a task for you, all right? Your grade as it stands right now does not incorporate number 5 at all, okay? Even if you got it right. So everybody has as homework to go home and do number 5 and turn it in on a separate sheet of paper first thing, beginning of class next time. If you turn it in and it is correct, right, then your grade will go up a little bit, okay? It'll go up just a little bit because I'll be grading instead of out of 4 problems, out of 5 problems. So it'll go up a little. But if you do not turn it in, or if it is incorrect again, then your grade will drop pretty dramatically. Does that make sense? Okay, so everyone understand what you need to do? Yes. Yeah, so a way you can look at it is if you don't turn that problem in next time, then you're going to lose 20 points off your test. All right, so that's a huge, huge impact. Now, if you did get it right, I know 1 or 2 people did, and I don't remember who it was, then all you have to do is turn your test in again next time. You don't have to go redo the problem, all right? And I believe it says it on there if there's a check mark. If you have a question of whether or not you got it right or wrong, let me know.
You have to redo it.
You do not have to redo it if you got it right. But you'll have to turn the test back into me to show me that you did it right. Okay, otherwise, based on just the first 4 problems, the class did very well as on a whole. I don't have the average and stuff for you today because I had a lot going on this morning, but it was, I'm going to guess that there were lots of B's and lots of A's. So I'll get the data together next time and we can look at it real quick. All right? Any questions on that, on the test? No? No? Okay. All right, well, we are going to begin some new material. We're actually going backwards in the book a little bit now. We're going to be looking at 11.2. All right, so this is always a very dangerous area that we get into in this class because we are going to start dealing a little bit with exponential and log functions. And students always have trouble with those. So let's start with a quick recap of exponential and log functions. This would be something you would have looked at in 1324. Right, so I'm going to put here recall. And when I put recall, that means this should be something you've seen before. That exponential functions are functions that look like this. A raised to the x, where a is greater than 0 and a is not equal to 1. Some examples of exponential functions. F of x equals 2 to the x. F of x equals 5 to the x. F of x equals 1/3 to the x. Do these look familiar? Do you remember seeing these in college, or not college algebra, in 1324? Okay, you should have graphed these also in 1324. You should have drawn graphs of these. They look like this. The graphs look like one of two things. So it's either this one, it's either this one or this one. So one of them looks like this. And you have like this asymptote over there. Or the other one looks like this. This was referred to as exponential growth, and this was exponential decay. Does this sound familiar? Okay. Now this happens whenever the A is bigger than 1, and this one happens when the A is between 0 and 1. So the A here, do y'all know what we call the A? It's called the something of the exponential function, the base. Okay, so this A right here we call the base. When the base of the exponential function is bigger than 1, you have exponential growth. When the base is between 0 and 1, you have exponential decay. And you also do have an asymptote over here. So this would be exponential growth, right? Because the base is 2. This would be exponential growth because the base is 5. This would be exponential decay because the base is 1/3. 1/3 is between 0 and 1. Okay? Yes? Yes? All right. So what we're going to be doing today is not graphing these or doing anything like that. We're going to be asking ourselves, what's the derivative of these? Which means we're really looking at, can you find the slope of the tangent line? Right? Can we find the slope of the tangent line? So, in other words, how do you find the derivative of something like this? What is the derivative of something like this? Now, I want you to be very careful here because, let me get rid of the graphs. Is that okay? Get rid of these? Okay. So, I want you to be extremely careful right now when we talk about derivatives. So, careful. If I give you f of x is equal to x to the 4th versus another function f of x equals 4 to the x, this is an exponential function, right? 4 is being raised to a variable. That's what this looks like, right? A number being raised to a variable. This is not an exponential function. This is what we call a power function or a polynomial. We have taken derivatives of this, right? What is the derivative of this? So if I were to ask you for the derivative of that, you would tell me the derivative is what? 4x cubed, right? Because all we did was apply the power rule. Power comes out, subtract 1, right? No problem. This, however, the derivative is not the same rule. Okay, so don't write this down because I don't want you to even put it on paper. This is not, well, what would happen? Bring the x down times 4 to the x minus 1. Maybe that's what you think it is. Like bring the power down and then subtract 1 from the power, right? This is completely incorrect, right? So that's what today is about. If this is not right, then what is the derivative of this, right? Okay, so I will give you what its derivative is. Okay, so let's put that right here. And then we'll talk about logarithms and after we get done with the exponentials. So derivatives, or the derivative of exponential functions. If f of x equals a raised to the x, then the derivative is equal to something here. You ready? Here's what it is. It is what is that? What's that? So that's not the final answer, but so far, what is that? It's the same thing. The derivative of an exponential function is actually itself, which is weird. All right? But then we have to multiply it by something. Times, I'm not going to say what that is, but do you recognize that thing? This right here? That's ln, that's the natural log. So you also studied that or talked about that in 1324, right? So we have natural log of this base. So let's do a specific example so you can see this. As an example, let's say you have f of x equals 4 to the x. Then the derivative of this would be what, according to this formula? So it would be the original function, right? 4 to the x, 4 raised to the x, times the natural log of 4. That's what it is. And what you need to understand here is that this right here is just a number. Okay, that's all natural log of 4 is. Natural log of 4, if you got your calculator out right now and typed in natural log of 4, it would give you a number. So this is just some number times our function, all right? That's all it is. Okay. How do you feel about that? Pretty straightforward? Just do not confuse it with the power rule, all right? That's the biggest mistake I see. Students will start trying to do power rule on exponential functions. You can't do it. So you have to recognize the difference between these. Variable is in the base. There's a number up here. Here it's switched. Number down here, variable up here. Okay? All right, let's do another one. Here's another example. Let's say that f of x equals 5 x minus 7 to the x. And I want you to find the derivative. So when we do this, can we do these separately? Yes, because there's subtraction between them, so we can do them by themselves. So the derivative of 5x is something we've done before, right? What's derivative of 5x? That's just 5. All right. Then we have subtraction, so I'm going to put minus. And then now, what is the derivative of 7 to the x? According to that, what is it? 7 raised to the x times natural log of 7. And that's it. All right? Questions? I think this section is confusing because you're doing natural logs and exponentials, but when it comes down to it, the actual computations it's not that bad. Okay, let's do another example. How about this one? F of x equals 5x times 7 to the x. That looks weird. Doesn't that look weird? Looks kind of like this one, except we had subtraction between the two here. What do we have between these two? That's multiplication. This is a dot, so that's multiplication. So how do you take the derivative of this? Product rule. Yes, exactly. Because you have multiplication there, you're going to have to do a product rule. So let's go ahead and do that over here. If you came in a little late, the tests are on the back table over there. All right, so if I'm going to do the product rule here, I have to do the derivative of this one, right, times this, plus the derivative of this one times this. So what's the derivative of this one? 5, we've already done that. 5 times 7 to the x, then plus, right? Product rule says plus. Now the derivative of this, which is 7 raised to the x times ln 7, or natural log of 7. I'm not done, right? Now times this times 5x. Now some things to be careful with here. This is not 35 raised to the x. You are not allowed to multiply these together because, remember order of operations? Remember this? You're always supposed to do parentheses first. We don't have any parentheses. Exponents always go first before multiplication, right? So you actually have to figure out what 7 to the x is before you can put it together with the 5. And you don't know what 7 to the x is because you don't know what x is. So you are not allowed to put those two together, understand? So you just leave it like that, 5 times 7 to the x. Over here, same thing. You can't put this 7 and the 5 together because this 7, you have to take natural log of it first. Make sense? So we could probably just leave our answer like that and be happy, be done. All right. Questions? Sure. Okay, let's take a look at a special case. Okay, a special exponential function. See if you remember this one. Remember that one from 1324? That was a very special exponential function. It's actually called the natural exponential function. Pardon? Yeah, and it has a very nice property when we take its derivative. So first, let's all make sure we understand something. E here is a number, all right? It's just a very special number. It's kind of like, you've seen this before, right? Pi. Pi is used to calculate areas and circumferences of circles and things like that. Pi is a very special number. It's about 3.1415, something like that. It's such a special number that we give a letter to it to represent it, right? We don't write 3.14. We write pi. All right. This is another very special number. Does anyone know approximately what E is? E is about 2.718. So I'll just kind of jot that down here on the side, just as a note. E is approximately 2.718. Approximately. So this is just a positive number. It's bigger than 1, right? Which means that this is exponential growth if I graphed it. But what's so special about this function is that when you take its derivative, well, according to the formula, you should get itself, right? Times natural log of E. Because the base is E, right? So we do natural log of E. And in 1324, you were probably shown this and you probably don't remember it, but this right here is 1. The natural log of E is 1. And that means that the derivative of e to the x is exactly what? E to the x. It is exactly itself. See, the derivative of 7 to the x was 7 to the x natural log 7. So it was almost itself, right? The natural log 7 kind of changed it a little bit. But e to the x is a function that is its own derivative. It's completely unchanged when you take its derivative. It's the only function that does that. There's no other function that behaves that way. All right? That's why it's so special. We were actually looking for a function that did that, and we were able to find it, and that's the one. That's the only one. All right. So let's do another example using that special result. Let's try this. Let's say f of x equals negative 7e to the x plus 4x squared minus 10. Let's find f prime of x. What do we got? What do you think? What are we going to do with that negative 7? What do you mean by nothing? It just comes along for the ride, right? Because that negative 7 is attached to the e to the x in the front. So it's just going to come for the ride. I'm just going to put negative 7 here. Now, what is the derivative of e to the x? It's itself, right? You don't have to write natural log of e down, okay? Just write e to the x. You're fine. And then I continue, because there's addition, I can take derivative of this next one. What's the derivative of this? 8x. And derivative of the last one? 0. So that's it. That's our derivative, right? Y'all all right with this? Y'all seem okay with it because y'all seem like I'm boring you a little bit, yeah? Okay. All right, let's move on. Let's talk about logarithmic functions.
So if the base is negative, it'll be a...
If the base is negative of the exponential function, like if that's like negative 2 to the x, then it's not an exponential function then. Because remember when I wrote down on the board, exponential functions look like a to the x, where a is bigger than 0 and a cannot be 1. Those are the conditions for the base. If you have a negative number here, then it's no longer an exponential function. Now, don't confuse that with this. I'll just show you a quick example. What if we want to take derivative of negative 2 to the x? Okay, this negative out here is really like a negative 1. All right, so this would look like negative 1 times 2 to the x. The negative 1 would come for the ride, and then you take the derivative of 2 to the x, which would be 2 to the x natural log 2. See that? This, however, the whole thing's being raised to the x. We don't deal with that. This is not an exponential function. It's a very complicated function. Who said that? The reason it's complicated, I mean, because you're asking, I'll tell you why. Just take a look at something as simple as, let's do negative 2 to the x. All right? Let's just try and create a quick t-table of what would happen here. If I plug in 0, 1, 2, 3, 4, let's try this. What's any number raised to the 0? 1. Okay, what's negative 2 to the first power? What's negative 2 to the first power? Negative 2, right? What's negative 2 squared? 4. What's negative 2 cubed? That'd be negative 8. And then negative 2 to the fourth would be 16, right? So if I try to graph this right now, look at how this would look. At 0, I'd be at 1. At 1, I'd be at negative 2. At 2, negative 2. At 2, I'd be at, what, 4? 1, 2, 3, 4. I'd be up here. And then at 3, I'd be at negative 8. Should be like down here. And then at 4, I'd be at 16, right? Like this. See how that's kind of like jumping back and forth? But that's not even the problem, because you know all the graphs that we've had have been continuous. We can pick them up, draw them without picking up our pencils. This one you cannot draw without picking up your pencil. It's not, we don't just connect these together. What's more interesting is like what's happening, like what if I plugged in 1/2? Oh shit, you're gonna be in big trouble here because look, -2 to the half really means the square root of -2. And now you're trying to take the square root of a negative number. Now you have imaginary numbers. It becomes extremely unstable. This function is very unstable. It does things that no function we've ever dealt with has had in it. Does that make sense? So we intentionally avoid these functions because they are so chaotic. Okay? The good news that those types of functions do not come up in the real world very, very often. Like we don't need a function that behaves that way. These, however, exponential functions, a lot of things in the real world behave exponentially. All right, logarithms. Logarithmic functions. So let me again recall what a logarithmic function is. A logarithmic function looks like this. We write log, we write a little subscripted a, and then we put x. Does that look familiar? Yeah? No? Okay. Does anybody remember what the relationship between an exponential and a logarithmic function is? Like, how are they related to one another? There is a relationship. Yeah, they're inverses of one another. Okay, so let me try and explain what that means because I think we need to have some understanding of that before we proceed. Let's take a look, and I don't want to do it over here because this is kind of a separate thought. Let's take a look real quick at this function f of x equals 2 raised to the x. What type of function is that? Exponential, right? That's an exponential function. Do you remember this picture when you're talking about functions, this picture that you were shown? Probably very in the beginning of functions where they show like, hey, the function takes things over here and then sends them over here. Yes? Okay, so let's say that the function that does this is this function f of x equals 2 to the x. Where would it send the number 1? Where would the number 1 go to if I sent it through that function? So 2 to the first power would turn into what? 2? Okay. Now, where would 2 go? 4. Where would 3 go? Careful. It would go to 8 because you're doing 2 raised to the third, not 2 times 3. So this would go to 8, right? Okay, that's dead. Where's mine? Ooh, good one. Right? Okay. Is there a function that would send 8 back to 3? So you plug in 8, it spits back 3. You plug in 4, it spits back 2. You plug in 2, it spits back 1. Is there a function that does that? Yes, it's a logarithm. A logarithm undoes the exponential. So the function that we would need to go back from there to there would be the log. Anyone have an idea of what the base of this log would be? What that number would have to be if we want to undo this one? We would need, no, 2, just 2. Log base 2 of x. That would be the function we need to undo it. So that's the relationship between exponential functions and logs. The logarithmic functions are the inverses of the exponential functions. They undo them. I was talking to another faculty member. I was like, how deep should we go into this stuff for this particular section? They're like, don't go deep into it because you're going to bury yourself trying to reteach them logarithms. And I don't think I can spend today reteaching logarithms. So I'm just trying to remind you of what they were, all right? This is the notation we use for them. And the question is, what is the derivative of it, right? That's what we're really interested in here today. So let's get to the derivative so we don't get bogged down in all that stuff. So what is f prime of x? Well, I'm just going to tell you what it is. The derivative of this, it's going to look weird. You ready? Is equal to, it's going to be a fraction. It's going to be 1 over x times natural log a. That's the derivative of a log function. So this number right here, this a, comes into play again in the answer. The answer is going to contain that natural log of a. Just like the derivative of the exponential had that little natural log of a in there, this also has a natural log of a in it, but it appears down in the denominator along with this x. Okay? So let's do a specific example. So as a specific example, let's say f of x equals log base 5 of x. Find f prime of x. So let's just follow the formula. According to the formula, we're trying to take derivative of log base 5 of x. The answer should be 1 over what? X natural log of 5. And again, natural log of 5 is just a number, and here's your variable x, and these two things are being multiplied together. This okay? All right. I think if I gave you a couple of others with different numbers in here, you could do this, yes? Okay. So let's talk about a special log function. There is a very special log function, f of x. What was the special exponential function that I just showed you a few seconds ago, a few minutes ago? What was that special exponential function? It was e to the x, right? Well, guess what? There's a special log function that has that same base, e. So it's this one right here. Log base e to the x. Or e, that's not e to the x, it's log base e of x. So this is the actual function that undoes that exponential function e to the x. This is the one that undoes it, all right? It's its inverse. This function is so special that we don't even write it that way. Like, that's not the way we write it down. We do this instead. We write ln x. Like, we don't even bother writing log and the base and then the x. We just write L and N. That's not an I, by the way, that's an L. Okay, it's like French. You know how the French reverse things in their language? So it's logarithm natural. Logarithm natural. Instead of natural, logarithm, logarithm natural. All right? So that's the notation we use instead of this notation. So when you see this, you need to understand that the base is e. Right? It's understood. What do you think the derivative of this is then? Well, go back to this and follow that. Well, the formula's gone. Sorry, the formula was here. What would the derivative of this be according to that formula? 1 over x times natural log of e. But didn't we already say just a second ago that the natural log of e is 1? So what does this at the end of the day really turn out to be? 1 over x. So the derivative of the natural log of x is 1 over x. Got it? Derivative of natural log of x is 1 over x. So e to the x and natural log of x are the real nice ones, right? Those are the real nice ones. If you wanted to, you could just summarize it this way real quick. The derivative of e to the x is itself, and then the derivative of natural log of x is 1 over x. Nice and clean, right? Derivative of e to the x is itself, derivative of natural log of x is 1 over x. That's it. All right, so let's try something here. Let me change it up. Let me go y equals x to the 8th minus 8 to the x plus 4e to the x minus log base 6x plus 4 natural log x. I've given you a rather ugly function there. I'd like for you to try and find the derivative of that. If you can find the derivative of this, then you basically are good to go with everything I've talked about up to this point. I'm going to give you a minute or two here. So I'm asking you to find y prime. Raise your hand when you've got it, okay? Just hang tight. I'm trying to get an idea of how long it's taking people. Just raise your hand when you've got it, when you think you've got the full answer, okay? Okay, you can put your hand up. If you need help or have a question, I can come help you. You got something? Sir. Yeah.
It would just be the 4 on the outside.
You can do that, or you can put the 4 on top with the 1, because that's really like a 4 over 1.
4 over 1 over
Yeah.
x.
No, like this. It's so that 4 is really like a 4 over 1. And then if you multiply these two together, you get just 4 over x. Make sense? Okay. Okay, I think I'm going to start writing the answer down up here and see if you're getting the same thing here. That's what you should have. So derivative of x to the 8th power, that's power rule. 8 comes out, subtract 1 from the power. Minus comes down. 8 to the x, that's exponential. So the derivative of that is itself, but then you have to tack on that natural log of 8. Plus 4 comes down because it's a constant attached. Derivative of e to the x is itself. Minus comes down. Derivative of log base 6 of x, well, derivative of log base anything of x is 1 over x and then natural log of the base. So natural log of that 6. And then the last one, the 4 comes for the ride, and then derivative of natural log of x is 1 over x. And I showed over there on the board that when you have 4 out front and then times 1 over x, that you can rewrite this as 4 over x, because the 4 just kind of slides up on top of the x. Good? Any questions? You all feel comfortable with that? Okay. Let's try something going back to, why we were taking derivatives a while back. It's like, what's the point? Trying to find slopes of tangent lines and things like that. So how about we do this problem? If we have, let's say f of x equals 2 times natural log of x, I want us to find the equation of the tangent line at x equals 1. So this has a graph, right? The graph of this, looks like something, right? Now I'll put the graph up here even though we don't need it. The graph of that kind of looks like this, if you were to graph that function. This is 2 natural log of x. And what we're trying to do in this problem is to find the equation of the tangent line. If we go to x is equal to 1, we're trying to find the equation of that blue line, the actual equation that would draw that blue line. So do y'all remember how to do this? What do you have to use to get this equation? You're going to need the derivative, right? You're going to be using the fact that that equation is going to come from this y minus y1 equals m times x minus x1. Tell me when this starts to look familiar. Yes? Do we know, or can we get the x1, y1? That's going to be a point on the graph, isn't it? Yeah? It's going to be this point right here. This is the point x1, y1. And then what about the slope of this line? Where does the slope of this line come from? From the derivative. Okay, so we have done this before. Yes? So let's find our derivative. Let's figure out what it is. What is the derivative of this function? Just 2 over x, right? That's the derivative of that function. It's the 2 comes for the ride, derivative of natural log of x is 1 over x. So if I'm trying to find the slope, I now need to use the fact that x equals 1 is where I'm looking at, right? So what is the slope of this line at x equals 1? It's just going to be 2 over 1, right? Which is just 2. So what you're doing is you're using the derivative, you're taking that x, you're plugging it in, you get 2 over 1, which is 2. So this slope that we're looking for of this blue line should be 2. So we've got that part. Do you all agree? We have this m. We're good to go on that m now. Do we know x1? Do we know the x coordinate of this point? Yes. What's the x coordinate of that point? 1, right? Now, the only thing we don't know is y1. That's kind of a question. That would be this y coordinate right there. How would we find that? How could we find that y coordinate? We could plug it into the original function. In other words, we could plug 1 into this, and wouldn't that tell me how high I am at 1? Right? So what happens if I plug 1 into this? So what is f of 1?
0.
F of 1 is 0. How do you know it's 0? Calculator told you, right?
Yeah.
Yes? Okay, so natural log of 1, my graph is wrong, by the way. Sorry, my graph, I drew that incorrectly. It should be like this. It should be down more. Sorry, for some reason I drew like a square root function. That's messed up. Okay, so 2 natural log of 1. You're going to need your calculator at this point, unless you know natural log of 1 is 0. So everyone needs to make sure you're comfortable with that natural log key on your calculator. Type in 2 natural log of 1, you get 0. Okay? So this is the point. If we come back here and fill everything in, it should be y minus 0 equals 2 times x minus 1. So just replacing this with 0, replacing this with 2, replacing that with 1, and then I think we're done. The left side is just y. The right side is 2x minus 2. Sorry? That's it. This is the equation of the line that is tangent to that graph at that point. All right. We have 2 more little topics to cover. I'm going to actually cut out a little early today because I've got to go meet up with the chair of the department about something. Properties of logs. So again, back in 1324, there were a bunch of properties of logs, and I'm going to put them up here and let's see if you recognize them, all right? Natural log of mn times n equals natural log of m plus natural log of n. Natural log of m over n is equal to natural log of m minus natural log of n. And then natural log of m raised to the r equals r natural log of m. Now honestly, do any of those look familiar? The first two? The first two say that if you have a single natural log and you have multiplication inside, that you may split this up into 2 logs with addition between them. This one says if you have a single natural log with division inside of it, that you can split it into 2 logs with subtraction. What is the last property saying? If you have natural log of something to a power, what can you do with the power? You can bring it out front. This is a very important property. You can bring it out front with multiplication. Now let me show you why these properties are so important. Let me give you an example over here, okay? Because I think up to this point everything's been pretty straightforward. I could be wrong, but okay, how about this? As an example, y is equal to natural log of 4x squared over over 7. Find y prime. Does that look complicated? That looks complicated, doesn't it? If you were trying to take the derivative of this right now, what you would have to do would be chain rule. Remember the chain rule? Where you start on the outside and work your way in? So what would the outside of this be? What would the outer function be? The natural log, right? But then on the inside, wouldn't you have a quotient? Okay, this is going to become a disaster. So before I take the derivative, I'm going to use some of these properties. You ready? Watch. Do you agree with this? Do you agree with that? Isn't that the same thing? I had natural log of 2 things being divided. So what I did is I split it into 2 natural logs with subtraction between them. Yes? Okay. Now, do you see that that's product right there? 4 times that. So couldn't I split this first log into 2 different logs with addition and still have that last log out here? Yes? Do y'all see it? The multiplication right there? Multiplication becomes 2 different logs with addition. Just take the 4 and then the x squared. Still good? Sure? Now, do you see that power right there? What can I do with that power? I I can bring it out front. See? If I have something to a power, that power can come out front. So I could also say that this is equal to natural log of 4 plus 2 natural log x minus natural log of 7. I've taken this whole thing and I've rewritten it all. I have not taken a derivative yet, right? But this should be the same as this, yes? Now, let's take a derivative and let's see just how clean it is. If we do y prime now, what is the derivative of natural log of 4? Now, don't go doing the 1 over thing. Think about this. What is natural log of 4? If you type it into your calculator, it's just a number, isn't it? So this is a constant, right? What's the derivative of a constant? 0. So derivative of that 0. Plus, now, you have 2 times natural log of x. The 2 is going to come for the ride. Derivative of natural log of x? 1 over x, right? So this is 2 times 1 over x. And then minus, what's the derivative of natural log of 7? It's a constant, so derivative is 0. So what's the derivative at the end of the day here? 2 over x. Isn't that a lot better than having to have dealt with like chain rule and stuff? Okay. All right, we're going to do one last problem, and then I'm going to cut you out of here. You will be able to do the homework from this. I'll try and get a video of the homework up. It's going to follow pretty much along with what we did in class here today. Okay, so I'm going to put up a function here, and I'll explain what everything is after I put it up here. So you have r of t equals 20,000. And then 0.86 to the t. Okay, let me explain what this function is. This function right here gives the resale value of a company car. T years after purchase. In other words, this has to do with depreciation. So you have a company and you're going to be using you're going to buy a company car, you're going to let your employees use it, right? And eventually you're going to sell it, right? Get rid of it. This is a function that represents what the value of that car is after so many years have gone by. Okay? So let's think about what the graph of this, I haven't even told you what the questions are yet, but can you tell me what the graph of this should look like? If this is t, this is time in years. It should go down. Now, can you tell by looking at the function itself what type of function this is?
Exponential.
It's exponential. Because you have something raised to a variable, don't you? Is this exponential growth or decay?
Okay.
It's decay because the base is smaller than 1, right? So that means it's going to look something like this, right? That's what it'll be. Now, time can't be negative, can it? I mean, you can't talk about you're going to buy a car. Nothing makes sense before the moment you buy it, right? So really the picture is only this side right here. Can anybody tell me how much we bought the car for?
14,000.
How much?
20,000.
How do you know it's 20,000? Kobe, what do we buy the car for?
What do we buy the car?
Mm-hmm. You just seem kind of out of it. You've been on your phone a lot today, so. Why, where are you getting 20,000 from?
The y value from the function.
It's this value, but I agree it's 20, but where are you getting it from?
Because that's where you're like starting out from, and then you're gonna.
Where are you, but I don't understand where you're getting that from, 20,000. I mean, I agree with you, but how do you know it's 20,000? Are you just looking at that number?
Yeah, well, it's the y function, isn't it? That's, I mean, that's the y-intercept.
Is that the y-intercept always? It depends. I mean, if I had like a plus 30 out here, it wouldn't be. Think about this. When you buy the car, what's time? 0, right? Time is 0. What would happen if this is 0? This to the 0 is what? What's this to the 0? 1. Remember, any number to the 0 is 1, right? Any number to the 0 is 1. So if you take 0.86, raise it to the 0, you get 1, right? 20,000 times 1 gives you the 20,000. So when time is 0, right? When t is 0, you get 20,000. That's how much we bought the car for. I just want to make sure everyone understands that the number out here is giving us the original value of the car, but it's because that's when time is 0 and this right here is 1. See, what I'm getting at is if I had, 4,000 out here as part of my function, then the original value of the car is actually $24,000. Make sense? Okay, so you have to be a little careful. All right, so I would like to know in exactly 3 years, I want to know what the value of the car is. All right, that's my first question. What is the value value of car, after 3 years? Okay, first question. B, same question. What is value of car after 10 years? So how are you getting those? You're just plugging in those values, right? You're plugging in 3 into that. You're plugging in 10 into that. So this is where you need to have your calculator, and you need to make sure you know how to plug these things in and make sure you can get these answers. So for part A, let me show you how we do the solution. For part A, we're doing R of 3, which is 20,000 times 0.86 to the third. And then for part B, we're doing R of 10, which is 20,000 times 0.86 to the 10th. So when you do this on your calculator, you have to make sure you type it in correctly. Let's see, does anyone have anything for part A yet?
12,721.
12,721 and 12 cents. Close enough, all right? About 12 grand after 3 years. Now, according to this function, this model, how much will it be worth after 10 years?
4,426.
4,426 and some change? 03, okay. Those two questions that I just asked you have nothing to do with calculus at all. That's just, hey, according to this model, how much is it worth after 3 years? How much is it worth after 10 years? Now, here are the calculus questions. What is the rate of depreciation at 3 years? And then the other question is, what is the rate of depreciation at 10 years? So just think about it this way. After 3 years, when you get to 3 years, is the rate at which your car is depreciating more than how fast it's depreciating at 10 years? What do you think? You think it's greater at 3 years? You think it drops off fast in the beginning and then kind of flattens out? I mean, think about if you buy a brand new car, which I don't recommend you ever do, unless you just got a lot of money to blow, all right? As soon as you walk out of a dealership, right, with the car, the value drops immediately, right? Because you've put miles on the car. And now it's not